Picture a big apartment building where every flat has its own furniture, its own posters, its own smell of dinner cooking. The tenants feel like they live in totally separate worlds. But there is only one set of pipes, one electrical system, one foundation under the whole building, shared by everyone. Each flat just decorates on top of that single shared base. A French family and an Italian family can both live there happily, because both only need the same plumbing, but you could never drop a houseboat into a flat, because the building was not built for it. That idea of separate-looking homes, all quietly sharing one foundation, is exactly how containers share one kernel with the host. People imagine each container boots its own operating system. That mental model makes container size, startup speed, and platform limits impossible to reason about, and it leads to confusion like, why does my Mac run a hidden virtual machine for Docker? An operating system has two big parts: the kernel that talks to hardware and manages processes, and the userland of libraries and tools that programs use. A container ships only userland. Every container process makes system calls straight into the host's single kernel, just like any normal process, so there is nothing to boot and no second kernel anywhere. A program does real work, opening files, sending packets, allocating memory, by making system calls, which are requests into the kernel through a defined instruction like syscall on x86-64. A container process makes those identical system calls, so the host kernel schedules it, gives it memory, and runs it exactly like a non-container process. Namespaces only change what that process sees when it makes a call. For example, getPID returns 1 inside its PID namespace, but it is the same kernel answering. Because the kernel is shared, the container image needs 0 kernel code, which is why a whole image can be a single 8 megabytes binary. This sharing is also the platform limit. An Ubuntu and an Alpine container both work on a Linux host, because both only need a Linux kernel, and their userland differences do not matter. A Windows or Mac OS host has no Linux kernel, so Docker Desktop quietly runs a lightweight Linux virtual machine and starts your containers inside that one shared Linux kernel. The kernel version matters. A container built against newer kernel features can fail on an older host kernel even though the image is the same. The shared kernel is also the main security trade-off. One kernel vulnerability can potentially be reached from inside any container, which is why SecOmp and capabilities exist to limit the calls a container may make. Run, unaim, are on the host and inside 3 containers running Ubuntu, Alpine, and Debian images. All 4 print the identical kernel version string, because there is literally one kernel, and the 3 distributions are just different bundles of userland files on top of it. The biggest misconception is a container is a lightweight virtual machine. A virtual machine runs a full guest kernel on virtualized hardware and is isolated at the hardware boundary. A container runs as ordinary host processes isolated only by kernel features, sharing the host kernel directly. That difference is why containers start in milliseconds and VMs take tens of seconds. Like flats that decorate over one shared foundation, containers do not boot an OS. They borrow the host's one kernel through normal system calls, and that single shared kernel is the source of their speed, their tiny size, and their security trade-offs. I demystify the line between containers and the kernel every day. Subscribe to Tech with Joel. Did you already know your Mac runs a hidden Linux VM for Docker? Comment if that surprised you. Subscribe to Tech with Joel.